So 4 years ago, I started this YouTube channel, this science YouTube channel, and I posted a video about the history of gravity. It's really interesting because it's about how, as humans, we started from knowing absolutely nothing about gravity to today, where we're using lasers to understand gravitational waves, or we're using the Einstein field equations to adjust our clocks. So it's really interesting because, you start from nothing, from absolutely nothing, and then 2 or 3 thousand years later, we have these really sophisticated systems for studying gravity. Yeah, so I'm remaking this video, all the animations, but I realized that the script itself, it's a really cool story to tell. So yeah, that's what this is. So yeah, gravity, it's the reason rain pours downwards or apples fall down trees. And for a lot of us, it's one of the easiest way to die in a video game. But it's not all about things falling down. It's because of gravity that clocks in Jupiter tick slower than clocks on Earth. It's also because of gravity that some regions in space-time are so intense that not even light can escape it, black holes. And it's also because of gravity that in some spaces in the sky, in the night sky, the places of the stars that we see, that's not actually their real places. So that's gravitational lensing, which is pretty trippy. Like, why is it like this? From gravity as being something that makes objects on Earth fall down, how do we even get to those ideas? So the first thing you think about when you hear the word gravity is that it's something that keeps us from flying out of Earth, for example. And this is really one of the earliest definitions of gravity. So Aristotle was a student of Plato, and both these guys wrote a lot of their observations down, observations about life and crap and all that shit. And the thing is that Aristotle was a bit more organized. He wanted to share what he knew. That was his goal. So it's not enough to just observe things and think about things. He wanted other people to understand his thoughts so that those other people can make more complicated thoughts, and it goes on and goes on. It's progress. So this is something that's brought up a lot when you talk about the history of gravity. It's that Aristotle said that things move because they want to go back to their proper places. So there's 4 elements. There's earth, water, air, and fire. And earth, well, it wanted to go to the center of earth, and water would kind of wrap around that earth, and air on top of water, and fire on top of air. Then 2,000 years later, Galileo said, okay, this is the definition, this is not enough. Like, how does air know that it's air and it wants to be on top of water? Shit like that. It's thoughts like these. So Galileo read a lot on Archimedes, unlike his colleagues who were reading a lot on Aristotle. So he thought from Archimedes's law of buoyancy that, okay, you have a liquid, and the less dense object, it takes more time to reach the bottom. So Galileo thought, okay, what about if you replace the liquid with air? It should be the same phenomena that you observe. And it is. And then one more time, another intrusive thought comes in. What if you just completely remove that air? These objects would fall down at the same rate. So this was him trying to explain the motion of objects on Earth. Then from trying to explain the motion of objects on Earth, he thinks about, what about other things in the universe? How do these objects move? So another thing that Aristotle talked about was how the heavens, the stars, these heavenly bodies, are separate from us here on Earth, separate from Earth, because they have their own rules. So people believed this for a really long time until Galileo pointed his telescope to the moon and saw craters on the moon. For some reason, 16th century people didn't think that, craters are perfect. For them, perfect meant smooth. So people started questioning, are these heavenly bodies actually separate from us? And we'll get back to that later. In the meantime, people still kept recording things they saw in the sky, mostly for making calendars or navigating using the position of stars. And Tycho Brahe is someone who is known for his accuracy in recording things. So he made a lot of really cool observations on things like the motion of Mars, or some dot he saw in the sky that later disappeared, which turned out to be a supernova. And this discovery of the supernova was really important because, remember, at that time people were like, what, the sky, the heavens, they're perfect, they don't change. And then he comes with his records of, yeah, they kind of change. So people were really questioning, are the heavens actually separate from us? But let's go back to that data about the motion of Mars, because this was the data that Kepler used to come up with his laws of planetary motion. After Tycho died, he used this data for coming up with laws. But anyways, so how are these laws about planetary motion by Kepler important about our understanding of gravity? It's because Isaac Newton later on asked, okay, we have these laws about how these planets move. What's that thing that's making these planets move? Spoiler, it's gravity. And he thought about it a lot, eventually coming up with his theory of gravitation. And I won't talk about Kepler's rules like I did in my video 4 years ago. What I want you to learn to understand right now is the bigger picture, which is, okay, so Kepler showed those laws of planetary motion, and then Newton was asking, okay, what made these movements possible? So there's a force two objects experience due to their masses. And this force is equal. This force felt by object 1, by object 2, it's equal. And this is the third law of motion. But these two objects, for example, would have different masses. What happens is that the acceleration experienced by those two objects, even though they're experiencing the same amount of force, their accelerations are different. So Newton, as he allegedly watched an apple fall down a tree, saw that this apple from this distance felt an acceleration due to gravity, a beginning of acceleration for us to observe that movement of the apple falling down. So Earth actually experiences the same amount of force, but because Earth is so massive, it gets accelerated by a really tiny amount in comparison to the apple that's tiny, that experiences a big ass acceleration, so that we can see that motion like, okay, it fell. Newton thought that this kind of motion should be the same motion for any other object in the universe. You know, okay, we were looking at this tree with this apple falling down. What if we looked higher? You know, let's look at the moon. How does the moon move? Remember when I said that at the time of Tycho, people said things outside of the Earth were completely separate from us? Well, Newton completely changed this. Objects out there in space are just falling in a different style, in a circly style, in their own orbits. Aristotle was wrong about how the heavens are a separate realm. And so was everyone else until 1687, when Newton published his work describing what the fuck gravity is. So Newton talked about the effects of gravity on the motion of planets, of comets, on things out there in space. But Einstein came in much, much later, of course, and asked, okay, but what's gravity? Newton talked about the effects of gravity. Einstein wanted to know, what is gravity? What are the ingredients of gravity? So 3 years after he starts working in the patent office, he introduces his theory of special relativity. And 2 years after that, the equivalence principle, which says that gravity is the same as acceleration. And for now, you're just gonna have to accept that. You can search that later on. But the point is that a year later, Hermann Minkowski comes to him and says, for special relativity to work, you're gonna have to include time as a separate dimension. What the fuck does that mean? But what's the difference between having 4D space-time and normal three-dimensional space? So imagine walking in a straight line and imagine walking at an angle. So your distance would be the same, but walking in a straight line, like that, you're limited to one dimension. For this walking in an angle, you actually moved in 2 dimensions. So you kind of split your total energy into those 2 dimensions. The analogy is, the faster we move, the more energy we have to put into our space dimensions to actually move. So it feels like we're putting less energy onto our time dimensions. So the faster we move, the slower time feels, which is a pretty wacky analogy, but for now, you get the point. Apparently, the ingredients Einstein was looking for to describe gravity was that idea of 4D spacetime and the equivalence principle. So this combination of those 2 things is what he called general relativity. But there were barriers, and one of them was that he had personal problems. But one of the other barriers was that he had to apply non-Euclidean math, which just means math on a curved surface, which is a pretty difficult thing to do. But in a span of 10 years, Einstein comes up with these set of equations that can transform coordinates while maintaining that equivalence principle. Of course, with the help of other mathematicians, a lot of help from a lot of people. His theory of gravity explained how things out there in the night sky, even though we think they're in this position, aren't actually in that position because of gravitational lensing. And he also was able to explain how Mercury's orbit is kind of weird. And there's a lot more that happened after Einstein introduced his theory of special relativity. You know, we have gravitational waves, we have Schwarzschild, I don't know how to pronounce his fucking name, Karl Schwarzschild. He calculated the possibility of space-time warping around massive bodies, in bodies like black holes. And this is the moment where quantum physics and gravity would have to interact a lot with each other for reasons that I don't know the specifics of yet. I'll find out later. But yeah, there's a lot of things that happened after this. And that's the topics of a lot of my science videos. But anyways, it's really cool to see how the story of gravity came about. You know, from knowing absolutely nothing to writing our observations down a lot, and some of them being really organized about it, to sharing that information to someone questioning, Galileo questioning, okay, is that really how things move? And then he just points his telescope to the moon and see craters, and the whole perception of how the heavens are separate realm, they're perfect, just got destroyed because we saw craters on the moon, we saw supernova that's supposed to be there forever, then it's not because of someone who was recording things in the sky really well. So it's this whole barrage of things, of people doing things, people asking why, people asking how, that we ended up with today, with a lot of technology about understanding gravity, with a lot of everything. Right now we have a lot of international research collaborations trying to understand gravity, trying to use pulsar timing arrays, to use stars as clocks, which is a weird thing to say, but that's true. We have a bunch of scientists using pulsar timing arrays to use pulsars as clocks in the sky to see if a gravitational wave passed by, which is really cool. I have a video about that. But yeah, that's the story of gravity, and I hope you learned some stuff. You don't have to memorize people's names, you don't have to memorize what they do, but the main idea is that they asked why a lot.